Greetings, you poor unfortunate souls. Are you taking us on a tour of under the sea or something? What you got going on behind you today?
You better believe it. You said we're going to do a tour of the ocean floor, so we went to Atlantis.
Oh, yeah, that wasn't exactly what I had in mind, but I'm digging it. Cool.
Graham, I feel like this is what the ocean floor looks like, right?
That's does it not?
I mean, I get all of my scientific information from Disney movies as well. So
I
I'm
did
pretty sure
too. Oh,
This is
Marissa,
definitely the first view I've ever had of the ocean floor.
Were you thinking something a little more like this?
Yeah, actually, I think that looks a little bit more accurate, maybe less fun and vibrant.
Yes, and less like castle-y.
It's a
Yeah,
little
where's
crap.
Atlanta?
Nice. Okay. So I kind of understand. We're not going the cartoon ocean floor route. We're going the like actual what we know about the science of the ocean floor on Earth. Is that what the plan is for the day?
Yeah, we'll get it a little bit more accurate than The Little Mermaid did.
Okay, cool. Sounds good. Well, I'm also just going to welcome everyone joining us today to our monthly Rockin Pop-Up. My name is Marissa Gomez. I'm the Public Programs Manager at the Santa Cruz Museum of Natural History, and we are stoked to welcome back, as always, the Geology Gents, Gavin and Graham. So let's get to it. What you guys got planned for us?
Thanks,
Right.
Marisa.
Yeah. All right. So, as promised, we're going to take you on a tour of the ocean floor. It's a lot of dark grays and browns, and we're going to be talking about geology, and it's all going to be great. And of course, we're thrilled to be looking at the ocean, the rocks down there, and all the cool processes that happen at the bottom of the seas.
Oh, Graham, this is going to be so fun. When we actually were talking about doing this as a Rockin Pop-Up, I realized that as a geologist, I kind of oftentimes just ignore what's happening on pretty much most of the ocean floor, besides where some of the cool stuff is happening, like volcanoes and stuff like that. But even then, these are the largest actual area by area places on Earth. And they're a lot of times ignored by a lot of the geologic community. And so I think that it'll be a fun little tour.
Yeah, I know we certainly had a blast putting this together. So let's dive on in. So, oops, of course I'm clicking wrong. So, Gavin, what makes an ocean an ocean? Is it salt water?
Well, Graham, I have taken a dip into very salty lakes oftentimes, so I don't think it's just salinity. You also have inland seas. Is it size? But then you grew up on the Great Lakes. Those aren't oceans, right?
They're not oceans, but it's big water.
It is big. So what is actually the scientific, I guess, definition of an ocean?
Yeah, so an ocean is something geologic. And you're like, okay, geology gents, Graham, Gavin, the ocean's not made of rock. But it really is a geologic feature, because when you get to the edge of a continent and into an ocean, there is a stark change in how the land is shaped and how it moves. So as you get to the edge of a continent, you get off the shoreline, you've got this kind of shallow continental shelf, and then it dives down really steeply along the continental slope and out onto an abyssal plain. And by the time you get to an abyssal plain, the Earth's crust has literally changed beneath you. Gavin, what's happened?
Well, Graham, you go from continental crust to oceanic crust. And I'm not making those words up. Sometimes geologists get the words literally. Continental crust, as we've talked about in previous pop-ups, is actually different. Like you make it by processes, and you change the actual crust. So oceanic crust is pretty much close to what you make when you just melt mantle, whereas continental crust takes a long time and these long processes. It's also much thicker. The oceanic crust is much thinner in position, and it is also much denser, right, Graham?
Yeah. And so you mix all these things together. You've got this tall continental crust, and you've got this thin oceanic crust, and their densities are a little bit different. And what it does is it leaves the ocean crust sitting a little bit lower. And because it's lower, it's just a basin, right? So it fills in like one giant planet-sized puddle. And that's how we get an ocean. Okay, so that's what an ocean is in the geologic sense. And then, we've talked a lot about what happens at the boundaries of an ocean. So sometimes you go right from continental crust to ocean crust without interrupting the plate. It's all still the same plate, and you just slide down the continental slope, and there you are in the abyssal plains. But that's a lot like what the Atlantic Ocean is like. But Gavin, we got something kind of different out here.
That's right. The Atlantic is called a passive margin, and that really just means that nothing really happens for a really long time. We know that things are happening on the Pacific margin. You get uplift, you get the San Andreas moving things around, and that's because the Pacific margin is actually at tectonic plate boundaries. And so 30 some odd million years ago, we had a subduction zone here. That's how you built California. Now you are moving the plates past each other. That's why we have the San Andreas. But again, this is sort of like at the margin between ocean crust and continental crust.
Yeah, but so this is what's happening at the edges of the ocean. But when we go right into the middle of the ocean, there's something incredible here. And it's another plate boundary. Gavin, what's going on at this plate boundary?
That's right, Graham. This is sometimes the forgotten plate boundaries, but these are plate boundaries, and they're called spreading centers because you're actually spreading the Earth apart there. You can also refer to them as rift zones. You have a rift in the Earth, but I like to call them MidOcean Ridges because, as we can see on this map down here, they are ridges or spreading centers in the Earth that occur in the middle of the oceans. And it's no coincidence that they occur in the middle of the oceans, right, Graham?
That's right, because these are the places where the ocean crust thins out to nothing. So it doesn't really show it in this diagram, but the ocean crust gets really, really, really thin at these mid-ocean ridges because you've got this hot mantle that's sort of pushing its way up. It's hot, so it's expanding. And as it gets close to the surface, it starts to melt. Because as you take pressure off of hot rock, it will actually melt. We call that decompression melting. And then once you've got melted rock, you are on your way to making a magma chamber and a volcano. So all along these ridge lines, you have these volcanic feeder dikes, these vents that are coming up and that are erupting lava out along the mid-ocean ridges and literally building crust all the time, right as we're speaking, at every moment. And I just think that's incredible.
That's so cool, Graham. And this is a good opportunity to remind the audience or show the audience or tell the audience how you actually make oceans. So if we were just to start off with Pangea and you have one big continent, you eventually make the Atlantic within some portion of Pangea. And that's because these magma chambers and these feeder dikes and this whole plumbing system you show here starts off in the middle of a continent, and it actually breaks up the continent. That's a rifting center, and as it keeps on spreading and spreading, you open up an ocean. So it's actually, you're making oceans here.
Yeah, that's exactly right. So the Atlantic Ocean is getting bigger every day. It's always growing. It's growing, probably a little bit slower than our fingernails grow, but it's still growing.
It's pretty cool.
Yeah. And so let's start by taking a tour of the mid-ocean ridge. Let's start with the very top of it. Gavin, what are these wild things up here?
Right, Graham. So you said you make ocean crust here. So this is what ocean crust is made out of. And if you go to the top, it's basalt. And that makes sense because basalt is what happens when you melt mantle. And so you have melted basalt, but this basalt is an interesting basalt, and it's interesting because of its shape. Graham, what are we talking about? Pillow lavas? What's that?
Pillow lavas? Well, it's when you're swimming at the bottom of the ocean. It's a lovely place to take a nap. No, these are these big kind of bulbous, lumpy looking rocks that form when lava flows underwater. Now, the bottom of the ocean is cold. It's close to freezing. It's really, really chilly down there, colder than any of the water out here in the near Santa Cruz. And the coldest water is the water that comes up from the deep, right? So this water is chilly, chilly cold. And as this magma erupts as lava, it's cooled off immediately. So they form these crusts, but there's still hot lava inside of here. And this video shows just how hot it is. So it starts kind of squeezing itself out of that frozen shell and keeps trying to move. And as it does that, it makes these weird, like sort of lumpy, wormy structures. And those are pillow lavas.
It's pretty cool.
I think it's so cool.
But Graham, what happens if you go below there? What about the things you call here these sheeted dikes?
Yeah, so you need something to bring lava up to the surface to make these pillow basalts. And so you've got these narrow and thin volcanic vents that are bringing this stuff up to the surface to form pillow basalts. And as those cool and kind of get pushed out with each step of growth of our mid-ocean ridge, they make these really tall, really narrow sheets. And whenever we talk about a sort of like upright sheet of magma in geology, that's what we call a dike. And so you get these just layers and layers and layers forever and ever across the ocean called sheeted dikes that are these vents that are feeding up to it.
Okay, but in terms of rock types, those are actually the same thing as the pillow basalts, right? It's just basalt, but it's the distinction is the shape. Is that correct?
That's exactly right. So as far as the rock chemistry is concerned, you couldn't tell them apart. They're super similar. But then when we go down to the place that's building these feeder dikes, this is where things get really fascinating. And some might even say out of this world.
Oh my goodness. Gabbro, troctolite. I don't even, it's so funny. This is one of these like sort of weird minerals that you don't hear about a lot. At least I don't, but I know what a gabbro is. So basically what's happening here, Graham, is that you are evolving these magmas, you're crystallizing off some of it, and you're cooling them really, really slowly, right? So you have gabbro, which is chemically pretty similar to a basalt, but then as you get to sort of deeper in there, you actually have peridotite, which is what most of the mantle is made out of, right?
Yeah, that's right. And so as you kind of go through this bottom portion of the ocean crust, this sort of layered gabbro part of it, you sort of slowly transition back into the mantle. As you go through this magma chamber. So you've got this mantle-like stuff that crystallizes out and floats down to the bottom because it's really dense. And so that's where you get your peridotites, your real mantle-like stuff. Up at the top, you've got stuff that pretty much is chemically like what goes up into these feeder dikes. It's gabbro. So it's like a coarse-grained basalt, takes a long time to cool. And then you've got this other funky rock that's tucked in there with them called troctolite.
That must be the troctolite.
which you pretty much find in two places. You find that there's always some geologic exceptions, but on Earth, you mostly find troctolite in the deep ocean crust. And the other place you find it is not on Earth. You find it on the moon. It's a common rock on the moon. That is sort of a special, peculiar product of all that weird lunar geology that we talked about a few months back. So yeah, when you get to the bottom of this, you get these really cool, funky rocks, and it's like nothing we see, these sort of ocean crust sequences. They're very peculiar when you find them on Earth's surface, and it takes some funky tectonic events to do that.
Yeah, interesting. But Graham, is that the only thing that geologically occurs at the bottom of the ocean? Is there other stuff?
Most certainly not. Gavin, let's scamper back up to the ocean crust interface for a second and see what's going on there.
Well, Graham, I think that basically we're looking at what's going on on the ridges, right? On the tectonic plate boundaries. And these are what we call black smokers. These things look like chimneys, right?
Yeah.
And so what's happening is that when you're at a mid-ocean ridge, we explained that you have mantle rocks getting really close to the surface of the ocean, not the surface of the water, but the surface of the crust. Mm-hmm. And with that melted mantle, you're also bringing up hydrothermal fluids, or basically salty water that originates from deep within the mantle. And when you bring up these fluids, you also bring up these weird elements, all these kinds of heavy metals and things like that. And when they hit the cool ocean water, they actually cause chemical precipitates. Those are the gents' favorite rocks to talk about, because they hit the water and they basically make minerals, but they make minerals in the form of the actual like spout or the sipper, like that they actually come out in, right? So these are forming in as like vent plumes, right, Graham?
Yeah, that's incredible. So these chimneys are kind of building themselves as the hydrothermal fluids billow up out of there and release this uh, smoggy looking smoky water full of sulfur and iron and all sorts of wild heavy metals that we wouldn't like if we were to drink it. But there are some critters that really, it's really quite a feast down there for some of them.
That's right, Graham, because we'll get into this a little bit later, but the deep ocean is pretty much devoid of nutrients. There's not a lot of nutrients down there, and when there are, it comes from above. So this is like one of the very few opportunities that nutrients comes from below. And that's why around these black smokers, you see all kinds of different like worm-looking life and corals and weird stuff like that all around these black smoker vents.
Yeah, and so a lot of times these are thought to be like kind of nurseries of life. They're these very kind of weird primordial places where you've got energy coming up out of the earth, and these critters are like, ooh, energy, we can live with that. And so there's these really interesting, really kind of odd and almost alien-like ecosystems that go on around these black smokers.
Yeah,
super cool. All right, Gavin. So we've covered kind of the top and bottom of the ocean crust. Now there's another really neat thing about the oceans. And one way we've been able to actually understand them so well is because rocks record magnetism. And I know we usually think, oh, magnets are made out of metal, but no. The Earth's magnetic field has all these wild, weird electromagnetic fields. And those will align little bits of iron when rocks form. So Gavin, what's happening? So when the ocean crust first forms, it's going to align itself with that magnetic field. But then Gavin, what happens?
Right, Graham. So as you said, paleomagnetism works in that the pieces of iron in a rock, specifically a volcanic rock, will align itself towards the Earth's magnetic field when it cools. So when we first make new ocean crust, it has a certain alignment depending on the area of the Earth's magnetic field. But the Earth's magnetic field actually changes with time. So as you're constantly making new crust at the MidOcean Ridges, and that crust is spreading away from the spreading center, as the Earth's magnetic field changes in position, those rocks are actually recording that changing in position. So you have these stripes of magnetic fields as you show here, or magnetic lineations of those rocks, because as they cool, they're pointing towards the magnetic field during that time when they cooled.
Yeah, and so the Earth's magnetic field, it flip-flops itself every, million years, few 100,000 years. You never can be quite sure, but it's flipped itself many times throughout Earth's history. And the ocean crust forms really slowly. So you'll get these bands for a little bit of time, and then they'll switch, and then they'll switch. And so folks have mapped the seafloor with magnets. They tow around ships and they look at what the magnetic field on the seafloor is. And they've actually been able to map out these alternating reversals through time. And so they use that to guess how old different parts of the ocean are.
That's right, Graham. We know pretty much when the magnetic field has switched on Earth. And so we can use it as a chronometer, basically. But this is also how scientists discovered that plate tectonics were actually happening. They took these amazing maps of the ocean magnetic field, and they're like, oh my God, that's a plate boundary right there. You're making new crust there. And so this sort of map has been really, really integral in earth scientists trying to understand how the oceans work and how you're making new crust. And Graham, it looks here that we have pretty much 300 million year old crust. Where is that happening in the ocean?
Yeah, so as we talked about before, everything right around these black lines here, that's all brand new. That is 0 years old, born today. And then the oldest stuff are those things that are right up against those passive margins, right? So you can imagine a time when you zip this whole thing back shut, you wind back the clock and you close this ocean. And so right here at sort of the boundaries of the ocean are where you get your oldest crust, or here, like out in the middle of the Pacific. But there's one really, really cool exception to this rule, Gavin. And where's that?
That is in the Mediterranean.
Right.
And so that's the Mediterranean is where you get the oldest rocks, or the oldest, not rocks, the oldest ocean crust. And that's because you kind of closed Africa up against the Eurasian continent, and you left a bunch of old ocean crust there, but there's no actual margin that's subducting that crust away. And so it's just kind of staying there. So they find like 350 million year old ocean crust in the Mediterranean. It's pretty wild.
That's amazing. We often think about the Mediterranean as this like incredible area of human history. And lo and behold, it's got plenty of great geologic history too. It's a pretty incredible spot.
So Graham, real quick question, just to bring this all back. The Earth itself is 4.5 billion years old. And the oldest continental rocks are pretty close to that, 4.2 billion. But the oldest ocean rocks are only 300 million. And so what's happening? Where are they going?
Well, Gavin, it's just what's happening a little bit up the coast from us and all around the Pacific. As new ocean crust is made, the old stuff gets gobbled up, gets subducted and eaten back up by the Earth beneath the continents in these subduction zones. So around the Pacific is where that's happening a lot. Here in where the Himalaya are forming, that used to be ocean crust that was getting gobbled up under there. Now you've got a mountain collision zone. But yeah, ocean crust in terms of Earth history, it doesn't hang around for very long. It's got a short lifetime of only about 300 million years. And you need a really special condition like in the Mediterranean to preserve anything beyond that.
Yeah, and it kind of makes sense, right? If we were continuously making Earth crust, the Earth would be getting bigger and bigger, and we know it's not. So it must be also being recycled and going away, and that's not erosion. It's actually subduction, and so it gets recycled back in the mantle. So geophysicists, this is a bit of a tangent, but it's amazingly cool, so might as well say it because we have time. Geophysicists use seismic waves and other sorts of imaging techniques to actually look and image old crustal slabs, they call them, basically old ocean crusts beneath the continents. And so we've mentioned in the Rockin Pop-Ups that we've had a subduction zone on the west coast of the United States for the past 150 million years. And there's a big slab underneath the continental US that's where all that ocean crust was subducted underneath. And we can actually image that, and it's pretty deep and it's pretty far inland into the US. So that's pretty cool. That's where the ocean crust goes.
That's so cool. Yeah, that's amazing. All right, so we've covered the middle, where we get rid of it, how we know how old it is. Okay, but if I go down to the ocean floor, am I going to always be scrambling around volcanoes, Gavin?
Actually, Graham, you're not. It's pretty much just sediment when you go to the ocean floor. So as you had mentioned before, most of the ocean is these abyssal plains. They're called plains because they're very flat in most cases. And it's a huge, huge area of the Earth. It's actually the largest by area type of environment on the Earth. And it's very flat, and it's similar actually to the moon in that it's got like a thick layer of sediment in it. And so, Graham, where does that sediment come from is the question.
Great question. It's coming from above. And because everything's above the ocean floor. But yeah, there's all sorts of really cool processes that go into bringing sediment to the ocean floor, because we're super far away, right? When we think about how sediment moves around on the surface of the earth, we often talk about rivers and landslides and yeah, well, mostly rivers.
Wind, yes,
Yeah.
igneous
And,
activity.
and there's no rivers down there, and it's a plain, so there's no hills to have landslides on. So the best way to bring sediment out there is by the wind. So Gavin, talk to me about how wind is getting sediments down to the bottom of the ocean, because I'm pretty sure there's no wind on the seafloor.
That's true. Well, as you said, it's coming from above, Graham. And the thing that happens on the surface of the earth a lot of times is that you get these huge dust storms and these big dust clouds that take these microparticles, these tiny grains, and they carry them hundreds of miles. They carry them all the way out to sea, and then they just float right down onto the surface of the ocean, and then they just sink right to the bottom. That's not the only way that you can get sediment to the abyssal plains, though. There's also really strong currents, ocean currents. That's this picture here on the right. Yep. And they can also bring some sediment off the actual coasts of the continents into the abyssal plains over time. You also have underwater volcanoes, as we said, not just at the MidOcean Ridges, but also actual volcanoes on the ocean surface. Those, similar to volcanoes on land, puff out a bunch of big clouds of sediment and ash, which rain down onto the surface of the ocean. But in terms of life and how we think about what shapes the ocean ecosystem, the ocean like underwater ecosystem at the bottom of the ocean, is this oceanic snow, this marine snow. That's this bottom right picture. And what's going on there, Graham?
Yeah, so, there's not a ton of life out in the open ocean, but there is some life. There are fish and critters that grow and live out there, and they make bodies, and they eat what they can, and then they get rid of that food as waste, and sometimes they die, and their bodies will sink down. And so this oceanic snow is all the bodies and waste and scraps and bits from all sorts of marine life that are just slowly trickling down through the ocean column. Sometimes there's critters at lower levels that will eat them, and they'll maybe only eat part of them. And so there's this whole sort of, exchange of organic matter, right? When I say organic matter, I just mean like, life stuff, things that can feed living critters or living critters are made of, and they eat and they poo and they do all that stuff with. And so it kind of slowly gets recycled down and eventually just rains down and lands on the seafloor at its final resting place. And so there's actually, there's not a lot of light, there's not a lot of warmth, so it's hard for critters on the seafloor to eat, but there is some nutrients. And so Gavin, what happens to that nutrient?
Well, Graham, as you said, there's not a lot of light, there's no oxygen at the base of the ocean. And so that's not great for making nutrients, but when the nutrients kind of fall and the organisms, mostly microbes, eat it all up at the base of the ocean, they just produce this stuff called methane. It's similar to what cows produce, but they make this methane. And again, it's so cold down there that methane is sometimes locked up. What do we call that, Graham?
Yeah, we call it a clathrate. So it freezes, the methane forms a crystal with water that freezes at the cold temperatures of the bottom of the ocean and under the pressures at the bottom of the ocean. So if we took a little chunk of methane clathrate up to the surface, it would boil away in our hands. And if we were to warm up the deep sea, it could also boil it away, but it's kind of just cold enough and just pressured enough that these things will form these really wild looking ices.
Right, Graham. And so that's sort of methane builds up at the base of the ocean. But what happens when you put a bunch of other sediment over it and then you crush it up a little bit with tectonic activity?
Oh my goodness, Gavin, there's nowhere to go but up. And you get methane bubbling up, and then it makes a methane seep. And Gavin, what do we love more than anything else in Santa Cruz geology?
The Swift Street outcrop. It's the coolest outcrop, and it shows this like very, very bottom of the ocean process. So you have this picture at the bottom left here, and those are the methane seeps that we're talking about at Swift Street in Santa Cruz. And what's happening is that over time, you have a bunch of these microorganisms. As we said, they build up methane when they eat, and they get buried, and you squeeze them up, and they finally make their way to the surface as these like big methane seeps, and they get fossilized in these kind of also bulbous, weird-looking formations in the mudstone above.
Yeah, it feels like we've almost come full circle to sort of lumpy rocks. We started with pillow basalts, and now we've got methane seeps, and
Right.
they're very different things, but look kind of similar.
Yeah, interesting. So, Graham, have we done it? That's pretty much what's going on in the ocean floor, most of it.
Yeah, I think we've done a pretty decent job, and I've just had a wonderful time this afternoon under the sea with you.
Oh God, it was great. The ocean has a ton of cool geology going on.
Yeah, it's more geologic than I would have thought before we started this.
Still probably not as cool as the land, but cool in its own.
But we might be a little biased as well.
That's fair enough. If we were sea creatures, maybe we would say the land is boring.
It's true. So now we've got an exciting announcement for our next Rockin Pop-Up. Gavin, what's the next Rockin Pop-Up going to be?
Oh my goodness, Graham. We've been waiting for this for over a year now. But next month in July, we're doing our first in-person pop-up in over a year. And I'm so excited, Graham.
Woo! It's going to be great. I haven't ID'd a Rockin person in so long.
I know. I cannot wait. So if anybody is out there watching and you have some rocks you want to ID, or you just want to come to the museum next month to talk rocks with us, we are just jazzed. So we're looking forward to it.
Yeah, we are so excited. Like you said, I mean, it's been well over a year now. I think the last in-person pop-up was February of 2020. And for those of you who have just started tuning in to these since we've gone virtual, Gavin and Graham have been doing pop-ups for the museum for like 3 years, and the vast majority of them have been in person. And they're great opportunities for people to bring in rocks that they've found or that they have questions about, or explore the museum's geology collection and learn more about local rocks through those resources. So we are stoked. So we'll share more information about that event in a bit. And thank you both so much for today's program. I was thinking a lot about the rocks that we have in California that are influenced by the fact that we are like right next to the ocean, and that we have that subduction zone aspect and all of the faults around here. Things like serpentinite, which we've talked about a lot, and then benitoite, which I'm not going to have you guys go into detail about that, because we have another geology event next week, which is with a professor at UC Santa Cruz that both Gavin and Graham work with, Hildy Schwartz, who's partnered with the museum over the years. And she's going to be talking to us about our state gemstone, which is benitoite, which kind of has to do sort of with what we've been talking about today, but kind of like more on the continental crust side of things. So
Hildy taught me everything I know about benitoite, so you all will be in good hands.
Hildy is amazing. I have gotten to go on a geology of the Central Coast field trip with her, and it was just life-changing. The whole reason why I love geology today is because of that field trip with Hildy Schwartz. So we hope that you Rockin Pop-Up fans will join us for that event, and I will add a link into the comment section of this video. And looking forward to having you guys back at the museum next month in July. Great. Okay. So we'll see you all next month, not virtually. We'll be back for the virtual pop-up in August. All right. Bye, y'all.